All right.
Hey, Charles, how are you doing?
Great, man. It looks like we're going to go a little native now.
Let's see, because
Okay.
I don't know. We're talking with Robert Griesemer here, who is one of the developers on the Go language.
Okay.
And let's see, whether he considers Go to be native or not, because I don't know what native really means.
Okay, well,
so let's
ask
figure
him.
that out. Let's ask him. So
Well-
what kind of language is Go?
Go is definitely a native language. We compile to native code, but it also has a scripty feel nowadays.
Exactly. So that's what I mean. It's like, where's the kind of, So, like, for example, let me give you an example. Let's go, because I want to really pull out what this native thing really means. Because for many people, native means not jitted. Is that a definition that you adhere to as well, or?
No, I would say native is if you have actually code that's run, if you don't run an interpreter.
If you don't run an interpreter.
Right.
So you would say that Java is also a native language.
To some extent, yeah.
Okay. And Haskell is also a
Because
native language.
if you run the JVM long enough, at
Yes.
some point it's pretty fast. But
Yes.
you have to run it long enough.
Okay. And so where does the scripty feeling from Go come from?
Well, if you just develop pure Go code and you never want to interact with some other stuff, which by now you can for a lot of things, we have now a fancy new build tool by Russ Cox, which takes care of building a large hierarchy of Go packages, without you having to describe how this hierarchy looks like using makefiles or anything like that. So you just point your Go build tool at the top level package and say, go run foo.go, and off you go. And what happens is your program is being compiled right then and there and run. And it's so fast that it feels like you're just running it interpreted.
Yes, because there's also the kind of try Go thing on the web where you can type in, like a Go program and
Right.
kind of hit run. That feels also extremely kind of scripty or like a little interpreter or
Right.
feeling.
Same
Yes.
thing happening there. So
Yeah.
we sent the source code to the app engine, basically, where it's being compiled and linked and then executed. Again, it's just such a fast, compile, link, run cycle that you don't notice that it's not interpreted. It's actually compiled.
Okay, so now let's kind of drill now a little bit into this kind of still the native versus non-native thing. So you're saying that the compilation is super fast. Why, like, when you distribute Go code, do you distribute that in source code or in kind of compiled form?
It depends. So you can, of course, download the whole. It's open source, so you can download the entire source tree and you can build it from scratch, and it will take 15-20 seconds or something like that.
But that's the Go.
That's the entire Go infrastructure.
Yes, but I mean, if I write a Go program.
If you write a Go program, you can. I think it depends on what your intentions are and what your, how you feel about your source code being spread around. Of course, you could just send around the source code, but arguably many companies will just send out a binary.
Okay, because I must say, I'm personally struggling with, why do people call something native or not? Because, if you observe it from the outside, if you're saying this thing compiles so fast, how do I know whether this thing compiles or interprets or if I run the program as long as it runs fast enough, should I care if there's an interpreter or a compiler or not?
I think as a user you shouldn't care, because who cares? You care about what this thing is doing, and how it is doing is somewhat unimportant to the user, I'd say. But of course for the developer, there are certain things that come with it, and one of the things that you get when you have a compiler that does all the work up front is things that like super fast startup time. You can memory map something, and things just come up much more quickly. And I used to work on V8 a little bit, and before that I used to work on the JVM, and you can play all those tricks to make the program not pay for stuff that you don't use and only pay for it when you use it. And so you can go really, really close to this, it runs instantaneously and almost as fast as compiled code. But there's always a little bit of a price to pay. And startup is one place where you
okay, so now we're getting somewhere. So it's startup time. So, and you're saying like tricks where you kind of, you run your VM for a little bit and then can do like a core dump and then you load that. That kind of gets you kind of close, but not really there.
All right.
Okay.
Pause, at this point, yes.
Yeah. And another thing that people, I think, often maybe implicitly associate with native is the fact that you can get like at the raw pointers and raw bits and bytes.
I don't think that is an aspect of native languages. You can do this in any other dynamic language too. I think if you provide the facilities. One thing that maybe is underestimated is the fact that if you have a natively compiled binary, it's not going to change.
Okay.
Okay, and you can deploy it on X machines, and it's going to behave exactly the same on all those machines. That's really important if you have a data center where you cannot have like a JIT on every core, and in particular you want to make sure that you have the same library set up everywhere, and you cannot rely on that. So that's a big plus if you have.
Okay, and so another thing in that same kind of spirit is that, say on your phone, you don't want to use battery life to JIT code where you could have, kind of compiled it somewhere else, because that's kind of in some sense unnecessary overhead if you kind of, compile it on your phone. Is that?
Probably true. I suspect this is like a place where things might change, but I'm not really an expert in that field.
Okay, so now let's then talk about another thing. It's like garbage collection. So is Go a garbage collected language?
Yes, of course. I think it's it's madness to program in a language that's not garbage collected these days. And yes, there's penalties, and we're working on them.
And so what kind of garbage collector does Go have?
Well, Go is if you will, is a better C. Okay? So it is statically typed. It has the basic types. It has pointers, but it has no pointer arithmetic. It has arrays, but it has array bound checks, things like that. So
all the good things of C are gone. Yes.
Everybody needs to choose his or her poison, I guess. So it's a safe language in that sense, and as a result, you also garbage collection is crucial when you want to program and you want to really do encapsulation the right way, and especially if you have concurrency, it's getting really, really difficult if you had to start thinking about who is going to release what at which time. So I think having garbage collection is just a must these days.
Okay. So another thing that I find super fascinating about Go is the way you deal with exceptions. So one of the things I'm kind of coming to the conclusion more and more is that, why are we actually even doing kind of null checks and so on? Because usually when something goes wrong, there's little you can do. So maybe the only thing you can do is just let the whole thing fail and then kind of restart or something. So, and Go has also like a non-traditional exception model. Can you explain a little bit about what your philosophy is there?
So I think in Go we believe strongly that a lot of the errors, they're actually meant to be handled explicitly. Okay. So if you open a file and it doesn't open, or there's something happening, you should really know about this error and you should handle it. You should be almost forced to handle it. Okay. And in Go, you have multiple return values of functions, so dealing with errors becomes much easier and sort of natural. And you have the choice to explicitly deal with this error. We even have an special error type in the language, just to make this extremely natural. But you have the choice, of course, to ignore it and do something else. We do have what we don't call exceptions, we call them panics, but essentially it's the same thing. But we wouldn't call the surrounding mechanism necessarily exception handling. We would rather say it's a mechanism to handle exceptional situations. And so we would like to really urge programmers to treat them as such, as opposed to using exception handling as a mechanism for control flow.
Okay, so let me then kind of make my so I really kind of agree with you, but I'm trying to kind of make my point a little bit more precise. Like if there's no file, yes, that's kind of something that you should handle. But say that you're doing like a check on when you're entering a method and you're checking whether this parameter is like within bounds. Wouldn't be another way to do it is to just kind of because at some point that will lead to an exception anyway. So why do you kind of check it early? Why don't you just kind of let the kind of exception happen at some point? Because it feels to me that if you're checking at every place,
so
you're still not ruling out the fact that things can go wrong.
No. I mean,
yes.
that maybe I didn't express myself clearly. I mean, we definitely have this mechanism. We don't check eagerly everywhere. Yes. Okay, but it is a matter of how you design your libraries. One philosophy might say. This API is built such that if something goes wrong and your input is wrong, you get an exception. And then you probably should declare that exception somehow because it's part of the API.
Yes.
In our case, because we do not don't have to declare panics, but we actually want to see these error situations, our approach to library design is that at the boundary, we will get an error back. Okay, that is a type, and you look for it's a value. You check for it if you need to. Inside the library, but it's a different story, and it's quite common that we actually use the panic mechanism, for instance, or yes, division by zero, for instance,
yes.
that might happen, but you don't want to have it go across your library boundary.
Yes, yeah.
So we use our try catch. Finally equivalent, which is quite different, to actually catch that error and then transform it into a normal, or that exception or panic and transform it into a normal error.
Okay, so one last question about exceptions.
Panic.
Yeah?
Okay.
So you mentioned that you don't want to encourage using exceptions as a control flow mechanism.
Right.
And a lot of people I think are saying that implicitly or explicitly, maybe because the exceptions are too slow. But on the other hand, I think exceptions are actually a very powerful control flow mechanism because they allow you to kind of it's like an extra continuation that you get. So why are people so opposed to kind of using exceptions? Maybe like let's not call them exceptions, right? Let's call them whatever, non-local returns or something like that. I think we're really leaving some money on the table by not giving developers the ability to use exceptions as control flow.
So I think this is perhaps a philosophical aspect of the whole situation. Some people believe this is the right way of doing it. We believe that's not necessarily the right way of doing it. I think there is some. I'm not sure that there is actually scientific studies that actually compare both paradigms and see and look what's better and what's worse. And but it's clear that if you have exception handling pervasively, for instance. There is implications on the kind of optimizations that the compiler can do because certain things have to be preserved. It's very hard to reason about your program because every function, to some extent, has to understand that it possibly may be returned through without the function dealing with all the things that it needs to do to clean up. And so if you make this a standard paradigm, I believe programming actually becomes much more difficult to not necessarily to do, perhaps to start with, but to understand.
Okay, so allow me to kind of ask one more thing, because if you look at the way we build data centers with chaos monkeys, where you kind of arbitrarily kind of make the thing fail.
Right.
Why shouldn't our code be like that, where you just assume that whatever you call it can just blow up in your face?
Again,
it's I feel that we're maybe not. To me, it feels not fractal enough, right? If we're building it in the large, we're doing it like that, and then in the small, we say, well, then I cannot reason about it, and doesn't feel right to me there.
Well, I want to say something different here. I think it is wrong to take one paradigm and just stretch it out all the way.
Okay.
I feel for the same way that I feel like it's wrong to say, okay, the object-oriented paradigm is the only paradigm, and then expand it to everything. Okay, it is one paradigm, and it has its very good uses and very good applications, but if you just use it as a matter of your philosophy, then you may end up at a place which is not necessarily better.
Okay, so
and so I think the same applies here. If you just say, well, we use exception handling in the large, which in Go certainly you can do. And again, in Go, if you want to use exception handling or panics as a control flow structure in your code, nobody's going to prohibit you from doing it. It's just that we don't recommend it. I think it is really our feeling is it is a mechanism for handling sort of large scale things and in our libraries we use it for some things, and then we say this is a boundary, and at this point we return an error, and people should know about it and deal with it explicitly.
Okay, so you're saying it's not turtles all the way down.
Right,
there might be kind of alligators or elephants or...
Absolutely.
Okay.
Yeah.
So the other thing that I found really nice about Go is the way you deal with interfaces. Can you explain a little bit how that works? The notion of interface.
Yes. Okay. So. Again, object orientation, there's a lot of ideas. I have talked to some friends in the morning, and I tried to come up with an analogy. Like in the 60s, there was a lot of parsing technology developed. Okay, there's a lot of theory about languages and how you can parse them, et cetera, et cetera. But at the end of the day now, 40 years later or more than that, there's a handful, maybe less, of actual parser techniques that are really in widespread use.
Yes.
And yes, we know we could do different things, but they're not really that important or relevant.
Yeah.
And I have, this is just a wild postulate here, but it seems to me that maybe the same thing might happen with the whole theory about object orientation and types, and there's some really cool ideas, namely that you have objects have encapsulation, provide encapsulation. Objects have mechanisms, methods with which you interact with them, and then there's a few other things, and other things that you need here are interfaces, which represent the class of objects, if you will. But it doesn't mean that this basic idea requires a lot of the machinery that has been brought in through type systems, etc. And so, as funny as it might appear, but the way object orientation is done in Go is very strongly inspired by some of the stuff that's done in Smalltalk, where you can just send a message via a method to some object. But now we have a statically typed language and has to sort of fit into a completely different space. So we came up with a different sort of approach. And so in Go, methods can just be attached to anything. Okay, we have basic types. We have arrays, we have slices, structs, and as you would expect. And in Go, you can just define a method and attach it to a function, if you want, the function type. You can attach it to your own integer type, if you will. Okay, and so those types then have methods. Now we have. On the other hand, we have the interface types, which are just purely specifications of method sets. Okay, and so if you have a variable of such an interface type, then you can assign to that variable anything that implements at least those methods that the interface requires. Okay, and so this makes it extremely lightweight. So a lot of code that you might write and start out with may not have any kind of methods at all. You might write it in a strictly sort of conventional style, and then you find out, okay, it's nice to be able to have methods here and use a dot notation. It's just a purely syntactical thing. There's no virtual dispatch or anything going on. And then you start dealing with classes of similar things, and you start introducing an interface, and you introduce it ad hoc. And the really important part is that you don't have to say, I'm going to implement this interface. It's a very sort of organic approach. So you develop your program organically. And one of the things that's really cool about this is when you have to interact with old existing code that you have no way of influencing.
Yes. Yeah.
And you need to interact with it. You can just create an ad hoc interface, even though there's no way for you to tell by the way, you better implement me, because it just implements it by the way you construct your interface.
And what happens now if if you want to implement, if you have two interfaces that happen to have the same method,
right.
How can you so you cannot distinguish between those?
No, two interfaces that have the same methods, they're virtually the same.
Okay.
But there's no. There's a lot of people that complained at first and say, well, what happens if I accidentally implement that interface? Isn't that like a disaster? And it's like, no, it's not. It just doesn't happen. And even if it happens, there's mechanisms you can exactly emulate the implements relationship. You just simply declare a method, I'm a foobar thingy, okay, and then everybody that implements I'm a foobar has to implement the I'm a foobar method, which is a dummy method. You get the same. You can sort of fake the implements declaration, if you will.
And so are you really saying that implementation inheritance is overrated? Is that?
I think that's probably true. I mean, I should say we have a mechanism to emulate, what one might do with inheritance in other languages. So we have embedding. You can have a struct in which you can embed another type, and then you get all the methods of that type, and again, they're being promoted to the level of your struct. So you can actually emulate inheritance very naturally and simply. You can also do things like forwarding and delegation, and all these things sort of fall out. Go doesn't provide these constructs on the language explicitly, but it provides all the primitives that you can build these things. So we try to focus on a few orthogonal primitives that you then can plug and play together as you like.
Yeah. So in that respect, the Go interface mechanism reminds me very much of COM, the old COM, because that was also very pure and interface based. And I agree with you. Similar. I think sometimes I feel that with object orientation we went overboard, like abstract base classes, virtual methods, sealed. It's like there's so many concepts and really what you in many cases all you want to do is you want to say, here I have an interface such that I know that I can expect that this value has these operations on it.
That's very much our feeling.
Yeah.
Yes.
So I really like that. So another question is do you guys have generics?
We don't have generics. So I think, of course, this is like a contentious subject. So there's lots of people that say, we're not going to touch this language until there's generics. And then there's the other group of people that say, we're not going to touch this language anymore as soon as there's generics.
Yeah.
We actually have an internal proposal, and we even have a sort of prototype implementation, and we have, I want to say, a couple of programs that work. I'm not the one who has been pushing it particularly, or I'm also not necessarily against it. It's just something that we are not, we haven't made any decision. And it's not necessarily clear that we need it, because it seems like we're getting fairly far with what we have.
Mm-hmm.
And the other thing is, we don't want to put something in that does not interact with the rest of the language as nicely as what we have right now, which we think we have some, we have a very nice set of features that work together very, very nicely, and generics will interact with all of them.
Yes.
So.
Yes, and then you have to make a decision whether you have covariance and contravariance,
right.
and
right.
so yeah. So it's interesting. I've been kind of hacking a little bit on the kind of .NET micro framework, which kind of has no generics, and it feels like I'm back in like 2000 when there was no generics, and it does have generics bring a lot of kind of they bring a lot of extra noise to. They are good on one side, but it's also they come with a very high cost. So. Yes, when you say, some people say I don't touch it if there's generics, or people that say I won't touch it if there's no generics. Yes, that seems to be like a kind of subtle balance to jug on.
But in C++, you don't have to use the templates facility,
right?
And it's a beautiful thing for library developers. So STL, the WRL, stuff like that. I mean, to me, it's like. it's kind of weird that people would say, if you added a template like compile time, genericity, blah, blah, blah to the language, I wouldn't use it anymore. That doesn't make any. Why would that be the case? Can you guys explain what you mean by it makes the whole language?
Okay, so let me give you an example, right? If you have generics, you always in some sense it's viral. So you're using a generic method here. Now the thing that uses that method has to become generic as well. So it's a little bit like monads in Haskell, where once you use generics somewhere deep inside, you have to kind of propagate that, because this thing is like now parameterized on a type, which is like an extra parameter, and then you have to kind of propagate that through your whole library. And look, I'm a very pragmatic guy. I don't mind to write a cast. If I know that this thing is an integer, just casting it an object to integer, I'm cool with that. So that's kind of my reasoning. And sometimes you can say, oh yes, it's more efficient because I know it's an integer, so I don't have to box it, or it's more type safe because I know that it's a list of int and not just a list. So there's a trade-off.
Sure.
But
if you design them right up front, right? So if you don't make the same mistakes that C++ made and that other things make, I mean, I don't understand why it's like an either yes or why is it binary?
It's not a yes or no. As I said, I mean, we have not made a decision yet. I think also I've programmed in C++ for 20 years, and I've used templates once in a while. And I should say, there's places where where they work, okay, but there's places where they just don't work. And one of the things is that people think they use a template, templated class or whatever, and a hash map or whatever, and they believe now, well, I got the speed, okay, because this has been inlined and everything. But there's example after example where it's not true. So first of all, you get an enormous amount of code load, even if compilers are very good and try to throw away code that's the same for different types, but essentially the same. So your caches get much bigger. If there is a bug somewhere, the error messages are used to be horrible. I think they're getting better, but still they're horrible. You have no clear understanding of what happens, really, because these templated hierarchies, they adhere more to, I want to say, the beauty of the underlying math than what they really should achieve. So I'm very, very, very skeptical. So I think they are. I personally used them when I had something small, which I actually wrote and which I had under full control, where the source code I can change it. Okay, I try to not use the STL because I don't know what's happening. I don't know where the time goes. If I need to fix something, you go through hierarchies of header files and you still don't know what the hell's going on. So I'm very, very, very skeptical. Now, I've made experiments the other way around and said, okay, how do I do this if I don't have generics?
Yes,
okay, and in C++, well, you have macros, and I'm not the person who is recommending you use macros, but this is your poor man.
Yes,
it's your poor man's template. Okay,
yeah.
And or you can use void, star, and things like that, and then you end up writing little wrappers. Okay, and it turns out when at the bottom line, at the end of the day, if you need to get something done and you want to have control over your speed and your performance and stuff, you end up with a piece of code that may be not beautiful in that mathematical sense, but it's probably shorter and clearer, and you have maybe one or two casts that are in strategic places, and yes, you can get it completely wrong, but it's maybe two places.
Yes.
Okay.
Yep.
So I think there is alternatives, and in the way it's done in Go, of course, we don't have macros. Of course, it's a bad idea. We don't have generics at this point, but you have empty interfaces into which you can stick anything, because there's no methods. Everything that has, a method or non, you can stick in there, and so you can take things out again, and you can type check. And so what you end up, if you write a container class, for instance, you end up with containers where you have to typecast at the end. And now if this happens a lot, write a wrapper. You end up writing 5 wrappers, 10 lines of code, and you get something that's maybe not aesthetically pleasing the purist, but it gets the job done, and it's probably easier to understand.
Yeah, and so Charles, that's another thing where I think we're talking about like a whole spectrum here, because if you look at generics like in Java and C#, that's purely kind of parameterization on types, whereas in C++ it's like also template metaprogramming. So it's this it's like I think when you're saying generics, it really kind of depends where you are on the spectrum, right?
So I think nobody in our team is against generics per se. Okay, it's just that nobody has come up with an idea that we all like and that really fits together well with the rest of the language and doesn't, explode the language in some ways.
Yeah.
And also nobody has approached us with some kind of an idea. And we have a proposal, as I said, and it seems not completely, bad, but we don't have really experience with it. We're going to play with it for a while, I suspect. Yeah,
and I think that's a good thing. So as a language designer, I think you have to be super conservative, because once you put something in,
you can never take it out.
You can never take it out. Right. Yes. So another very cool feature of Go is the Go routines.
Right.
I think the name is a little bit cheesy, but that's okay.
Well, the name is natural. Once you have a language that's called Go, and an implementation that's based on coroutines.
Yes. So yeah, can you say a little bit about what is so special about them, how they are implemented, and what is the use case for them?
Well, so this is the Go routines. They're coming in. They're coming in from via Rob Pike. I mean, he's played with them in different forms, but essentially the same idea in languages he's developed in previous lives. And again, Go was developed as an alternative to C++ from our point of view originally, and we wanted to, put in the mechanisms that you nowadays need in modern systems programming, and so we need strong support for concurrency, and this whole idea of the coroutines was a natural thing to pursue. Now the basis, the real origins, and of course go back to Tony Hoare, to CSP, and so what we have is really coroutines or processes in CSP and channels. And so a coroutine is essentially a coroutine. Okay, they can be preemptive, but think of it as a coroutine for now. And we have a single statement, the Go statement, which launches a function as a coroutine. Okay, and that's pretty much it. They are implemented on their own stacks. The stacks are the Go runtime manages the stacks separately, so they're not the usual thread stack they're segmented stacks.
Okay.
So they're very small, like I believe it's 4K at this point. So when you launch a Go routine, you really consume almost no resources. And the number of Go routines you can launch is only bound by the amount of memory that you have. Yeah.
And so what happens now because you say you kind of manage your own stack for the Go routines.
Right.
What happens if you call from the Go routine out into some external library that uses the regular stack,
well, then you have an interface issue, of course. Yes, you have to do some kind of a handoff. So we have various. That's not just an issue because of the stack. It's also an issue with the garbage collector and things like that.
Yes,
so
exactly.
I think this is an independent issue.
Yeah.
But we have. It is possible fairly easily to call to C and C++ code. It's harder at this point to call back, to call from C code and call Go. Okay. One of the reasons is the runtime, the garbage collection, and thread handling. Yes.
Yeah, and so another thing is, I kind of 100% agree with you that we need to have this kind of very lightweight way where you can spawn thousands or millions of these whatever processes or whatever you want to call them. But I always wonder, why doesn't the operating system, because it feels like every language implementer, every runtime implementer is kind of working around the fact that the operating system threads are too heavyweight. Or am I wrong that I want to kind of have that be part of the OS? Or is that something that the language runtime should do, or should the OS have cheap threads?
So I am not an OS person, and the evolution of OS is probably much smaller than. It's a slower running evolution than the language, development evolution, and so OS is originally had processes, and then you got lightweight threads and green threads and things like that. So they move in that direction, but I am not the one who is going to predict what's the future in the development of OSs. It turns out, of course, nowadays with the typical web programming that you do, you really want to deal with lots and lots and lots of threads, and so there's a natural limitation with OS-provided threads, because they come with a large stack to start with. There's kind of an overhead when you switch between them. You just need to get rid of them because you want to have thousands, hundred thousands of these coroutines, and so we ended up implementing them ourselves in user space. So.
But that's what Haskell does, Erlang does,
right.
And so it feels like that's like a typical thing that you want to move a level down.
I wouldn't be surprised if this eventually becomes, a general principle that is accepted by everyone, and then maybe OSs provide some mechanisms. Okay, but again, you can implement much of this in user space, so maybe the OS doesn't need to be involved. One maybe indication that things are changing a little bit is. We have two compilers. One is based on a Plan 9 C compiler that eventually morphed into the Go compiler, and there's a compiler based on GCC called GCC Go, written by Ian Taylor, and he managed to get the segmented stack support into the GCC framework. So this is something that might come up.
And so you said the Go routines can be preemptive. So how do you kind of switch between them, and how does that kind of work when can they block, say, on I/O, and then how do you kind of make sure that you kind of continue back to them?
So first of all, in the Go, you launch a Go routine, and off it goes, and at that point, you have no way to talk to it anymore. So that's where the channels are coming in.
Okay.
So a channel is essentially a FIFO. With synchronization, and you have the choice between synchronized or buffered unsynchronized channels. And what you usually do is you provide when you launch a Go routine, you provide it with a channel to communicate with. Okay, so the channel may be used to give the Go routine signals, and so you can send any data type through a channel, or it can also be used for the Go routine to return results, for instance. So channels and coroutines work together extremely nicely. I'm not a person who is very familiar with writing multi-threaded, heavily parallel code, but I can write code using channels and coroutines, no problem. It's very easy to reason about them. Yes, you can still have deadlocks and things like that, but you don't have to deal with explicit synchronization. The motto is communicate to synchronize, don't synchronize to communicate. And I think it has worked out quite beautifully. So I can write a thread scheduling pool in 7, 8, 9 lines of code in Go. So there's not even need to write a library for things like this. You just write it ad hoc. It's very simple.
But so one of the things is you make a distinction between like a regular method and a Go routine that communicates over channel.
Right.
But wouldn't it be possible to kind of just expose like a Go routine with a regular method, but that it's like more like an active object that kind of because my feeling is that you now make a conceptual distinction between a Go routine and a regular.
No, that's not true. So
is
again,
that true?
No, this is not true. So again, Go is all about orthogonal concepts that you can combine, in ways that don't interact in non-orthogonal ways.
Yes.
So we have methods and we have functions, and we have closures and all these nice things. And then there is a method to launch any of them. A Go routine can be a method or a closure or a function. It doesn't really matter. Now you could come up with another mechanism that interacts with all of them, and then it's not orthogonal anymore. Now that's one point, and the other point is would it be better to have something like an actor-based model or something like that? And I think there's different philosophies. There's all kinds of things that come into play, like are if you have actors, are they isolated? Do they have shared memory or not? And there's design decisions to be made. Now, this is a systems programming language. We want lots of threads, but we also want to have shared memory. We don't want to have to marshal huge data structures just to get them over a channel and then unpack them on the other side. So we share memory, and we handle that the access control, if you will, by sending over a capability. So we say, if this coroutine is done with this data structure, then we may send back a pointer to this data structure, and at that point, this coroutine is going to promise, I'm going to leave it alone.
Yeah.
Okay, and then this coroutine can pick it up and do something with it. And yes, this is a convention, and you can make mistakes, but it works. I want to say it works surprisingly well. The future has to tell whether it's a good idea or not.
Yeah. So I 100% agree with you on that, on the pragmatics of that. But I'm talking more about the programming model, right? Because why is there a difference between sending a value over a channel to a Go routine? I want to just expose that as just calling a method on some object. So I don't think there needs to be a conceptual difference between a channel and a Go routine and calling a method.
So you want to make everything a channel and a method?
I would make everything a method. And then the channels, that would be just like, there's certain special objects where I call a method, it kind of goes and kind of, to this, over a channel to this thing that runs concurrently, or it's just the fact that there's now two ways to interact with my values or my objects.
I see.
Well, and that is always the kind of feeling. It's like, why is the one so more special than the other? Because really, I'm just sending messages to these things. A method call is just sending a message to an object.
So if you want this model, of course, you just build it.
Yes.
Okay. You can write your nice little wrapper that looks to the outside like this model that you want. Again, Go is a systems language, and we believe in providing the programmer with the actual primitives.
Okay.
Okay. There is, if you look what happens at the end of the day, when the bits hit the bare metal, I mean, there is constants, there is variables, there is code that's being executed, there is types that really exist only mostly for the compiler, except when you take reflection into account.
Yeah.
So we expose those things. Okay, so we have constants, we have variables, we have types, we have functions. And those are the elementary building blocks, and so we have threads, Go routines, and so you take them and you build higher things out of them. So even if you think about something completely different, think of a different language like Smalltalk. Everything is completely uniform. Mm-hmm. But if you go down to the bottom, at the end of the day, when you hit the plus of the integer plus method, and you look inside that method, if you have a nice implementation, it does something like, self call primitive with the Y argument. Okay, this thing is actually there even in Smalltalk. It's just that it's not the thing that is propagated up. We don't tell people, write your code using this primitive. We say use always the wrapper, and if you wanted to, you could do this and Go, but that's not necessarily the recommended style. Does that make sense? Yeah,
that makes sense. All right, so I think this is great. So and I'm also happy to say that you just the port for Go on Windows is now, I think, official or finished or whatever. So
and I'm happy to say this was done entirely in the open source. So this was entirely done outside of Google. So which is great.
So now everybody can try and use Go.
Does Go have a async story built in?
Oh, that's the
that's our async stuff.
Yeah, that's
so that means you could write a projection for Windows runtime.
I think it's I'm looking.
Yeah.
Right. I'm looking forward to what people are going to do with it.
Yep. All right. Thank you.
Great to meet you. Thanks, Erik.
Thank you very much.
Thanks.
Yep.
Thank you very much.
Thanks.
Yep.